Okay. Hello, everyone. I hope you've had a good conference. Our last session of the day of day 2, in the last session of the North American part of the program. And my name is Michael Garry. I'm the editor-in-chief of the shecco's Accelerate Special Issues and online news sites. I'd like to welcome you to the Industrial Refrigeration Case Studies session. Happy you could join us online today. We have an excellent session in store with 3 very different presentations about very different technologies used in the industrial space. So looking forward to that. Reminder, you are encouraged to ask questions through the chat function, through the question tab, not the chat tab, because if you ask in the chat tab, we won't see the question. So put them in the question tab. We also have a polling question. Franco, could you show the question, the polling question? Is that available?
Yeah, give me 1 second.
Okay, so we have a polling question, which is you can access right next to the questions tab. I encourage you to address that question, and we'll give some results at the end of the session. This presentation and all others will be available after the conference, so you'll be able to refer back to it. And wait another second for the question. Has to do with the energy efficiency.
Here we go.
Okay. Yeah, compared to HFC or R22 industrial systems, natural refrigerant systems are generally more efficient, somewhat more, the same, somewhat less, much less. So I'm just curious as to the response to that polling question when you get a chance during this session. So now we'll introduce our first presenter. Pleased to have with us John Miranda of M&M Refrigeration, who's going to talk about the Hannaford Distribution Center conversion from R22 to transcritical CO2. John is industry-leading expertise in transcritical CO2 and CO2 ammonia cascade refrigeration systems for industrial refrigeration and industrial cooling. He's had a long, illustrious career, having worked at GEA, GEA, BAC, Guntner, Emergent Coal Technologies, and now at M&M Refrigeration. So we'll turn it over to John.
Thank you, Michael. Do I have to share my screen again, or do you see it?
No, well, you have to share it again, John, just like you did
a
second ago.
I'm sharing it again. You see the title screen now? I just want to make sure that I'll be good.
You got it.
All right. Hello, everyone. In today's presentation, we'll walk through the transition from an R22 refrigeration system to transcritical CO2 refrigeration for the Hannaford Distribution Center in Shattuck Landing, New York. This is near Albany. Before I get started, I need to give special thanks to James Baisley at Hannaford and Joe Stump at Mullally Brothers for making this project reality. Also, I'd like to thank Tommy Dolwick, Jesse Adam, and George Primo at Carnot Refrigeration for their support in making this a successful project. All right. Slides aren't moving. Little technical difficulty. The transition from an R22 system should be pretty evident due to its high GWP of 1820. R22 has been phased out. So the servicing of R22 based systems has to rely on recycled or stockpiled quantities of R22 which have grown in price from, $1 a pound 20 something years ago to over $20 a pound today. In today's presentation, we will cover the project scope, the transcritical CO2 system and technologies employed, the energy efficiency measures that were taken, as well as first year energy usage comparison of the two systems. Starting right to left on the aerial picture, we have two mechanical equipment rooms located above the brick office buildings, which are located on the dock side of the distribution center. On the roof, we have penthouse evaporators, air-cooled condensers, valve stations, and system piping for the existing R22 system. Screw compressor packages and recirculator packages for each of the R22 systems are located in the mechanical equipment rooms. So the challenge is to install the transcritical CO2 system while the existing refrigeration system is still in operation. Since we are utilizing the same mechanical equipment rooms and condenser steel structure for the transcritical CO2 system, we will have to phase in each refrigeration rack system. To accomplish this task, we will have to utilize hung style evaporators and pipe the evaporators inside the building. Let's look at the building loads. The refrigeration loads and temperatures are indicative of a standard grocery distribution center, ranging in temperature from a -50 freezer to a 60-degree banana room. The loads in tons are located in brackets besides each room. For example, the refrigeration load for the -5 freezer is 172 tons. If you go down the list, you can see that quite a few tons for this facility. Of special interest is the 55-degree dry dock heating coil, which is located in the dry storage distribution center adjacent to the refrigerated DC. This coil will use heat reclaim from the transcritical CO2 system for heating in the wintertime. Let's take a look at the transcritical CO2 system. The transcritical CO2 system utilizes high pressure CO2 racks and heat transfer equipment. That's all right. So I'm sorry. Utilizes high pressure CO2 racks and heat transfer equipment, as well as piping. So what does high pressure mean? All the piping and valves within the racks are designed for 120 bar or higher. Both the low stage and high stage compressors are transcritical types, which means they're designed for 80 bar on the suction and 120 bar on the discharge. The flash gas bypass receiver and intercooled vessels are all designed for 80 bar, allowing for high standstill pressure. All the evaporators and air-cooled condensers are designed for 120 bar and constructed with stainless steel tubes and pipe headers. The piping for the system was all 304 stainless steel tube or pipe per ASME B30 1.5 guidance and requirements. If you look at the pictures, we have somewhat of a transition from the R22 engine room to the transcritical CO2 engine room. And one of the things that jumps out are the size of the pipes. When you look in the right picture where the two racks are, the pipes are in black insulation, really small in comparison to the R22 lines. If you look down at the condensers on the roof on the steel there, you can see that the piping on the R22 air-cooled condensers is magnitudes larger than the air-cooled condensers on the right. You can see the largest line there is 2 inches compared to 5-inch, and in some cases 6-inch, and in other cases 8 inches. So let's take a look at the energy efficiency measures we incorporated into this system. So transitioning from R22 to transcritical CO2, we had no water available. So we had to go air cooled. And as we know, that's a penalty for transcritical CO2. And as a result, we incorporated several energy efficiency measures, which I'll call EE measures. First, we included oversized evaporators and gas coolers equipped with EC fans to save fan energy. In both cases, the maximum fan speed is 90%. This is part of the gain we do on the fan side. We take the evaporator fan energy savings even further with evaporator zone control. As the pictorial illustrates, we utilize evaporator fan zone control for all rooms and docks. Even our coil that's doing some heating on the dry storage has zone control for that space as well. So leveraging the heat reclaim advantages of transcritical CO2, we are optimally dehumidifying the freezer docks, which you can see they're under zone control, not only for temperature, but also for humidity. We are also providing heating of the high temperature docks. So, you know, if you move through this facility from freezer to cold and then cooler, in the wintertime, especially in Albany, New York, the docks get cold in the wintertime. So instead of using gas heating or electric heating to facilitate heating of the docks, the evaporators become heaters, and we heat the docks with the heat reclaim from the transcritical CO2 system. And of course, we provide underfloor warming and what we call efficient hot gas defrost, and I will cover that in the next slide. On the medium temperature racks, we have incorporated ejector defrost, which utilizes an ejector to pump flash gas from the flash gas bypass receiver for defrosting. Basically, the ejector replaces the compressor, and it helps us manage flash gas in the flash gas receiver. Oh, I forgot one. Yeah, and another EE measure that, of course, on the defrost side is demand defrost termination, which minimizes the room heat load penalty during defrosting. And of course, we float the head pressure down to as low as 50 degrees, which is very easy to do with the transcritical CO2 system due to its pressures. So the slide that I went to prematurely is a snapshot of the P&IDs for Rack A, which is taking care of the freezer. Rack A employs a high pressure 2-stage transcritical CO2 system with intercooling that provides the following, right? We have 50-degree liquid from the flash gas receiver, and at 50 degrees at 652, so that being at a higher pressure, that 50 degrees is subcooled through a subcooler prior to going to the medium temp evaporators. And of course, at the intercooler, we provide liquid feed at approximately 12 degrees to the low temperature evaporators. And then, of course, after the intercooler, we're subcooling that liquid about 8 or 9 degrees, so that, to increase the refrigeration effect at the low temperature evaporators. If you take a look at the left side diagram, there's a little loop at the top of the page. This is where all the heat reclaim is done. And you can see that all heat reclaim is supplied and returned on the high side of the system. This includes hot gas defrost as well. So in this system, when we go into hot gas defrost, there is no compressor penalty for recompression of the return condensate / vapor from defrost. We actually when the condensate returns back, it actually mixes with the superheated gas and it reduces the heat load going into the gas cooler. And we actually save some fan energy when we're in defrost. So let's take a look at how ejector defrost works, because for a grocery distribution, this is really important where you have a lot of medium temperature loads. If we look at the simple P&ID on the left and follow the green line out of the gas cooler outlet and then follow it to the inlet of the ejector and then discharge from the ejector into the receiver, which is the flash gas bypass receiver. And then we exit with the green arrow going up. And we follow that green line until we go into the inlet of what we have identified as PHE, which is a plate heat exchanger on the heat reclaim side of the system. At the PHE, we superheat this gas. And on the outlet, we have a red line. And this red line supplies the superheated gas to the medium temperature evaporators for defrost. And of course, the return from the evaporators are the blue lines. This is the condensate / vapor mixture returning from defrost. This returns into the suction side or the low pressure side of the ejector. The rack picture on the right shows the location of the ejector. So you can see this is a mechanical ejector that is set up and fine-tuned at startup, and it's not touched again. And then if you follow that ejector, I put in a couple screen captures of the actual P&ID. And so in the first one here, where I got the arrow going around, you can see the ejector being fed from the high side or from the gas cooler outlet. And then in the bottom picture, we can see the plate heat exchanger where we control the superheating of that gas prior to going to the evaporators for defrost. So let's take a look at the energy usage, and we'll talk a little bit more about ejector defrost and the benefits it provides there. So if we take a look at the 12-year energy data provided to us by James at Hannaford, you'll see that starting last year in August, we commissioned Rack A, and over up until May of this year, we basically phased in Rack A, Rack B, Rack D, and Rack C. And so we don't have a full year of operation with all 4 racks operating, but the energy savings today year over year are about 12%. We're expecting 20% energy savings when we get a full year of operation. The biggest area where we'll get additional energy savings is from all 4 racks working, or I should say operating through the winter. This is an area where CO2 does really well and where we have over 3,000 hours of 50-degree condensing and over 4,000 hours at 60-degree condensing temperature. The other energy savings will come from ejector defrost. So whenever the ejectors are defrosting a medium temp evaporator, and we have measured this on other projects, we see about an 18% improvement in COP because we have the ejector removing the flash gas instead of a compressor. So we will see the greatest energy savings from the ejectors in the summertime. So it's kind of ironic that the system will provide its greatest amount of energy savings on the compression side in the wintertime, but in the summertime, the ejectors will contribute. And I finish with the energy.
Thank you, John.
You're welcome.
That was very interesting. Are the ejectors part of that energy calculation, or is separate?
Now the ejectors are because of the way the system was phased in. we designed the medium temp with both hot gas defrost and ejector defrost. And so we're going to enable the ejectors here shortly on the ejector defrost side. So we have not experienced any of the energy savings from them yet. Yep. And good question, Michael.
And what additional savings on top of the savings you're already getting do you expect from the ejector defrost?
Well, we think the 11.6% will grow to 20% on a year-over-year basis. So you're looking at another 8 or 9%. Okay. With the ejector defrost, the energy savings are only when you're in defrost, right? Yeah. So it's a large facility, but unfortunately, we don't have an evaporator in defrost every hour of the day. So, I think when you look at the contributions from ejector defrost, maybe at the medium temp level, we're like we have 4 to 6 hours of defrost a day maximum.
Right. That'll bring it up to the 20% savings.
Yeah. Now, I mean, the biggest savings will be winter operation. Yeah. Where we're able to run at 50-degree condensing, both for the freezer, and we won't be able to run that low on the medium temp. 60 degrees is the low as you can go because you have a minimum compression ratio that you need to maintain, and then you end up with too much mass flow through the discharge valves on the compressors.
Is the ejector defrost, is that unique to Carnot? Is that
Yes, it's unique to Carnot. Marc-Andre patented this a couple years ago. And his thinking was, if you look at ejectors that were being developed for the marketplace, they were really only for the warm months of the year, right? To remove the flash gas from the flash gas receiver. And his thought was, why don't we have the ejectors work year round? And so, I'm eating popcorn and watching football. He's designing ejector defrost.
Well, he has his hobbies too, I think. So.
Yeah. No, I
think he's
a cross fitness guy now. So
I think he's into fishing actually.
Oh, he's a crazy fisherman. So
yeah. Okay, thank you, John.
You're welcome.
Our next speaker, and we'll have more questions at the end. Our next speaker is Kurt Liebendorfer, VP, Vice President of Evapco. Kurt is leading the development and market introduction of the new Evapco family of products, which are complete packaged low charge ammonia refrigeration systems. Kurt's been in the industrial refrigeration, process cooling, and construction industry for 30 years. And he's an active member of IIAR, as well as the Global Cold Chain Alliance. So then, over to you, Kurt.
Thank you very much, Mike. Michael, you can hear me?
Yes.
Okay. Share my screen. Success?
Yes. Well, yeah, you have to. There it is. Yeah.
Good?
Is that it, Franco?
No, that's like the. It's like, do you have two screens, Kurt?
I do.
Yeah, so this is like the, for like when you're presenting on stage. So I would just leave it. I would just leave it like this and just try to make it a little bigger or something. The two screen thing sometimes gets messy. So I would just leave it like this for now.
Okay, very good. Thank you very much. Kurt Liebendorfer with Evapco. All right, now I gotta advance my slides. Okay, did it advance?
Yes.
Yeah.
Okay, thank you. My case study is entitled How FUJIFILM Replaced R22 chillers with more efficient low charge ammonia chillers to expand their process. I want to make two quick introductory points. This presentation is specifically about a chiller, a secondary fluid glycol chiller package, which is one of the Evapco products. The presentation you saw this morning with the Shamrock that had a chiller in it, but 30 of those units were the other Evapco product, which is direct refrigeration with the penthouse evaporators. So with that being said, the other point I wanted to make is this is a story. So this is an actual case study that we had a third party conduct, and they interviewed several stakeholders within the project. So I've actually got some quotes through the project that I'm going to read with the various stakeholders, from the owner to the engineer to the installing contractor, inputting into the case study. So this low charge ammonia chiller was part of an expanding process that was conducted by Waco Chemical. Waco Chemical USA is a wholly owned subsidiary of FUJIFILM. The facility is located in Richmond, Virginia, and specializes in the production of antibodies, enzymes, molecular biology, and bio and organic chemicals. During a $35 million expansion in 2017 and 2018, the facility had a primary R22 existing system, and it became inadequate and was replaced and upgraded with 2 Evapco LCRC low charge ammonia chillers to handle increased production and provide redundancy. The plant's production processes required a nominal 67.5 tons of cooling with a 5-degree Fahrenheit 50% ethylene glycol solution, with occasional peak loading above that 67 tons loading. Some background. We needed to create cooling capacity and provide a level of redundancy, said Daniel Fry, plant purchasing supervisor and business operations leader. In addition to that, we needed extremely stable cooling capacity. Cooling capacity for the main process loop was originally provided by an R22 chiller system, and it resided in the circled building, as you see in the aerial shot. During the project's initial design process, the specifications developed by Waco and their engineer called for an in-kind replacement to include a larger R404A HFC chillers to replace the old R22 chillers. So they initially set out on this project thinking they would do the old R22 replacement with the newer HFC of 404A based on the temperature range. So again, the story here with the project team, I received a request for quote from Waco's consulting engineer, Richard Owen, senior processing engineer at Advanced Process Systems, said Chris Newman, who is a partner in Mid-Atlantic Refrigeration and for 25 years been the Evapco representative and focused on almost exclusively on industrial refrigeration. And the Waco facility, the FUJIFILM facility, and APS are their account. Waco is a longtime client of Advanced Process Systems, and Owen was an integral part of the entire plant expansion. For nearly 2 decades, Advanced Process Solutions has served clients around the globe, providing API, active pharmaceutical ingredient manufacturing, specialty chemical, and biofuel engineering services. So two critical stakeholders in implementing this project. So the development of the specifications. Owen with APS originally sought freon equipment, but saw an opportunity to specify a natural refrigerant given the need for the 5-degree F process fluid temperatures. We considered the possibility of installing an ammonia-based system, even though this project was considering commercial freon equipment, not industrial. Owen was instrumental in performing the original evaluation of the ammonia system versus an R404 synthetic refrigerant system. Once the evaluation was completed, it was the clear advantage of the Evapco LCRC low charge ammonia chiller that became evident through that review. So a little bit about the Evapco LCRC solution. The Evapco LCRC chiller product line contains over 200 models with available capacities from 20 tons to 400 tons, covering a chilled fluid temperature range of 5 degrees F to 50 degrees F. Each unit is completely piped, wired, and insulated for plug-and-play installation, including starters and single-point 460-volt electrical connection. Variable screw compressors provide efficient capacity control and part load operation. These packages offer numerous benefits over stick-built ammonia systems and Freon chiller package systems of similar capacity, including lower energy consumption, especially in the low temperature glycol application that was called for at WACO. In addition, they are available with several optional accessories, such as the fluid pumps actually mounted on the package, a waste heat recovery system. You saw that being utilized at the Shamrock project for doing underfloor warming and the tempering of the banana rooms. Outdoor enclosure packages are another option, along with there's multiple serviceability options available with these packages. The Evapco solution we provided with the LCR chiller was a prefabricated, pre-engineered, factory tested product, said Newman. We couldn't have accomplished that with a Freon package for a 5-degree application, let alone a stick-built ammonia system. And we took total acceptance of the revised specifications for ammonia, and the units were shipped in April of 2018. Looking quickly at some of the materials of construction of these industrial packages, it includes stainless steel piping, which is a big deal. XPS owns Corning Formular insulation on all the piping and vessels where insulation is needed. And all the structure is galvanized steel for great corrosion protection. And they feature industrial grade components from OEM suppliers Bitzer, Danfoss, WEG, RVS pressure vessels, and Kelvion plate and frame heat exchangers. Selection and performance. As I mentioned, two 67.5 ton Evapco LCRC ammonia chillers providing 5-degree F, 50% ethylene glycol, returning at 15 F with a -1 compressor suction temperature and a total of 135 tons of capacity. The flow rate to the plant's process load was 194 GPM from each chiller, or 388 GPM total for the two chillers. And of course, the cooling tower providing the cooling water at 408 GPM in at 85 and out at 95. So the evaluated COP for the Evapco unit with ammonia, low charge ammonia, was 2.49 at the design point and -5 or +5 glycol temperature. And the evaluated comparison with the 404 was a 2.14, again, you know, the best in class alternative at the time. So the Evapco chiller was evaluated at 17.8% better COP than the best in class competing Freon unit. So looking at the project site and the application, the new larger chillers replaced the existing R22 chillers within the same space of the utility building shown on the right there. So this utility building housed the old R22 system, which was smaller. And the new Evapco chillers, the two of them, were placed inside this existing utility building in the same space. So, and both were 7 foot wide by 13 foot long. Chiller packages were easily installed in the utility building in the same location as the smaller R22 system. There was a good rapid installation. The final installation and commissioning was handled by Colonial Web, a full service industrial firm with branches providing construction, building services, industrial refrigeration, manufacturing, and building automation services from 7 locations throughout the Mid-Atlantic. The chiller systems were piped to 2 existing pump skids and a hot well, cold well tank without requiring much work, said Andy Brogan, sales engineer for Colonial Web. 1 pump skid for the process loop and 1 for the condenser fluid loop, leading to an open cooling tower. Startup and commissioning. I conducted startup and commissioning of the chiller, said Brogan. This was the first Evapco system I had worked on. I wish more plants would go this direction for their refrigeration needs. These units are user-friendly, easily maintained, and based on the quality of construction, they'll last a long time. Being a critically charged package system, there aren't an abundance of components scattered throughout the facility. Everything is localized and easier to work on, which mitigates the problems typical of field-erected systems. Brogan started each unit, charged each unit with 80 pounds of ammonia, or 160 pounds for the whole system. Given the total cooling capacity of 135 tons, he was surprised to find that the system only required 1.18 pounds of ammonia per ton. Very low charge. Immediate use. Because Waco Chemical is a full production facility and there was no backup cooling system for the R22 chiller system that it replaced, the new ammonia system was put into service immediately. This occurred in August of 2018, and the system has performed flawlessly since. The two identical units are almost entirely redundant. Brogan explained that one system runs 24/7, while the second may come on for an hour or two a day in the height of the summer peak season. He manually switches the lead lag positions monthly to keep the equipment lubricated and balanced runtime hours. Waco has been more than satisfied with the new system, said Brogan. Results, real process improvements. In addition to better cooling and easier maintenance, we're no longer dependent on R22 for this main process loop, said Fry with Waco. An ammonia system like this one has energy advantages in that regard as well. After more than 2 years in service, there has only been one issue. A glycol valve became inoperable and needed to be replaced. Package systems like those made by Evapco provide lower life cycle costs due to decreased energy usage, lower refrigerant costs, improved compliance, clearly defined operating and maintenance procedures, and industrial grade manufacturing components. That's the conclusion of my presentation. Thank you very much.
Thanks, Kurt. So the first two presentations were both retrofits of these systems. Are we seeing more retrofits in these natural refrigerant installations versus new plants?
No, I would say, slightly more new plants, but yet plenty of retrofits,
Yeah.
Maybe 60-40.
60-40. Yeah, I mean, that's 40% retrofits is a pretty, I mean, compared to, say supermarkets, they don't do retrofits of natural refrigerant systems at a 40% clip in the retrofits. I think it's much lower than that, right? So that's interesting.
I mean, industrial systems, will last, hopefully forever. Call it, the average quoted time is 30 years. So, there's, in addition to some drive to replace the HFCs and the R22s, there's also a lot of end of life equipment out there that leads to retrofits.
Right. Yeah.
In conjunction with, there's a lot of new greenfield projects, which is the 60% at the same time. So I'm happy to see it successfully applied to both new and retrofit.
Right. Okay. All right. Now this is a water-cooled plant. Is that correct? Is this?
Yes.
Okay. Whereas the Shamrock one was air-cooled.
Correct.
Yeah. So is it more necessary for these chillers to be water-cooled?
Well, from a historical standpoint, most of them are. I say that there's plenty of air-cooled Freon chillers out there. It could be either. Low-charge ammonia being applied air-cooled is an evolving, growing new technology that is historically replacing what had historically been the type of condensing in central plant ammonia, which is evaporative condensing. And these packages really allow the air-cooled to be effectively applied because you can put small condensing capacity on each package. And that is what successfully made air-cooled prevalent in the Freon world. That's now happening in the ammonia world and is one of the technology reasons why packaged low-charge ammonia is growing in adoption, because it can be air cooled.
Right. Because people tend to not want to use water if they can get away with it.
Correct. And in the Waco chemical, it replaced old R22 chillers that were water cooled, already had the cooling towers. They could keep them and reuse them.
Gotcha. Okay. All right, Kurt, thank you very much.
Thank you.
We'll move on to now our last presenter. Let's see, how are we doing on this poll? We have 24 votes. I encourage more votes to come in. Franco, what's the result so far for this?
So we got much more efficient is 58%.
Okay.
So it's by far the winner because the next one up is 21% and it's somewhat more efficient.
Okay, great. Well, that's, we're seeing that borne out by these presentations with the energy savings, very significant energy savings in both of the case studies so far. All right, so last but not least of our speakers is Fabio Aloisio of Zudek.
Hello.
Hello. Good to have you. Let me give you give a little bio on Fabio. He's mechanical engineer with Zudek, has 10 years of experience at Zudek Refrigeration, has been working there since graduating. He's a key player in the research and development of Zudek's water ammonia absorption chillers. So here we have a completely different type of technology, absorption chiller. Take it away, Fabio.
Yeah, thank you. I will share the screen. Can you see that? Can you hear me?
Yes.
Okay, very good. So as a micro presenter, I'm Fabio Aloisio of Zudek company from Italy. And today we'll speak about water ammonia absorption chiller and their application in refrigeration. Some words about our company. We are located in Trieste, in the northern part of Italy, near Venice. And our mission is to propose and make a high quality solution for refrigeration, so machine and plants. And with a high quality system, we want to make high efficiency solutions. A solution that can grant energy savings and user-friendly system and with a low maintenance cost. And so for this reason, we found as a most suitable solution the use of ammonia as a refrigerant. Let's say our company has 30 years of experience starting from compression chillers. So we, let's say, developed our first water-cooled unit with inverter. And then we also supplied it with a remote management system to ease maintenance to the customer. Then in the early 2000s, we developed our first ammonia heat pump that was able to produce hot water up to 190 degrees. Then in 2008, we manufactured our first air-cooled ammonia chillers with microchannel panels condensers. So it's a plug-and-play unit that has the advantages of compactness of the air-cooled chillers, but the efficiency of an ammonia refrigeration plant. In 2013, we had two new technologies, and the one was mainly aimed for the dairy factories and the cheese factories, because of these companies have a very high consumption of icy water at 33 degrees. And usually they make this with ice banks, ice storage. So we developed a system who can supply constantly this icy water, allowing the customer to save 50% of the electricity. It's a standard compression chiller, but it's a new type of system for the icy water. In the same year, we developed the water ammonia absorber, but let's say it's something new, but the absorption cooling is, let's say, the most ancient technology for cooling because it's around, it was born in 150 years ago. But now it's becoming cutting edge for a lot of reasons that we will see very soon. In 2016, we provided our first safety system for big ammonia plants. So reducing the ammonia leaks in the air coming, for example, from the machinery room. And in this year, we commissioned our first air-cooled ammonia chiller with semi-hermetic compression. Let's say all these solutions are made around the customer because we know that each customer, each plant has its own needs, specific needs. And so for this specific requirement, we need a specific solution. And so for this reason, we made design and engineering and consultant with the customers in order to make a tailor-made plant or machine for them. Machines that we prepare here in Italy in our factory. And of course, we give always assistance to our customer with our maintenance team. So now I wanted to go more deep in detail about the case study of CO₂. CO₂ is a big and processing company situated in Verona, in the northern part of Italy. And as you can see from these figures, the company has a big energy consumption in terms of electricity, more than 7 billion kilowatt hours. And a big part of it is for refrigeration, more than 1 million. And so we can say that the coal energy in a year is more than 850,000 tons of refrigeration. Of course, also for the M processing, the customer needs also heat at high temperature. And so for this reason, he had to consume every year 200,000 cubic meters of natural gas. So if we want to analyze a bit this data, we can see that we can imagine that the electric bill of this company will be very high. And a big part of it is done by the refrigeration. And so this can become an issue, especially if we consider that the electric tariff is increasing year by year. So if we think about what was the cost years ago and what is the trend and what will be in the future, we see that having a system of standard refrigeration, so with refrigeration with compressors, have very big power consumption. And big power consumption means, of course, a high cost in the end of the year. So what we propose to CO₂ was a three-generation system. A three-generation system is a system that allows to produce in the same time electricity, heating, and cooling, also at low temperature. So the idea was to install a gas turbine, burn natural gas to produce electricity. Of course, this turbine gas has a waste heat at high temperature, and we can recover heat because we can make heat at high temperature, and heat can also be converted with an absorption chiller into cooling at a low temperature. So let's say the absorption chiller allow to make it with a low power consumption, because the difference is this. Absorption chiller use as a main drive for cooling heat, while standard compression system use electricity for the compressor. And so for this reason, the three-generation becomes a suitable solution to install absorption chiller. These chillers are based on the property of ammonia that is very soluble into water. So for this reason, instead of using a big compressor for make cooling, we will use a small water ammonia pump for the same capacity. But a small ammonia pump means also very low electricity consumption. So we can cut the electricity bills for refrigeration about of 90%. So there are, just to make a resume, there are two big classes of absorption chiller. One is the most common is the water and lithium bromide chiller that is mostly used for air conditioning or for high temperature process like plastic process. But water and ammonia is different. Works very well and is the only technology to go under 42 degrees. Down to minus 60 degrees. And so we can use it for a wide range of application. For example, the dairy and cheese industry, food and beverage, so breweries, wineries, meat processing, cold rooms of every kind, but also for chemical and pharmaceutical at low temperature, and also for ice creams and frozen products. So here it's just a resume of the installation. So on the top part, on the top left, you can see the customer was using a air-cooled chillers that was providing glycol at 70 degrees. There was an intermediate tank and a secondary circuit going to the cold rooms. So we installed, and you can see on the bottom left side of the slide, a capstone turbine of 1,000 kilowatt electricity that was able to give also heat at high temperature for steam, and the part of the heat was used to make superheated water, and this superheated water was converted into cooling. So just to give some data, if we consider 1,000 kilowatt electricity, we will be able to recover 1,250 kilowatt of heat that can be used for steam, 250 kilowatt, or for the absorption chiller. So from 1,000 kilowatt heat, we will be able to make 142 tons of refrigeration cooling. What is the good thing of such system? We said, okay, we install this because they are very cost effective. We can save energy, but in which way? We can see now with a cross comparison from a standard unit with 142 tons, and this system will consume each hour 200 kilowatt electrical kilowatt, and the COP, kilowatt on kilowatt, will be around 2.5. If we check the power absorption of an absorption chiller that is run by heat, we will see that the electricity is much less. So with these data, we can save around 90% of electricity for the same cooling capacity. So in the end, with this 3-generation system, the customer was able to produce for himself, self-produce electricity, but also at low cost, because burning natural gas to run a gas turbine for electricity is cheaper than buying from the net. Of course, this turbine gas has waste heat, but this waste heat is valuable. Is no waste, is valuable because we can use for cooling and for heating. And such systems have a very small maintenance, because an absorption chiller is a static machine. The compression is big, noisy, you need a lot of maintenance. Absorption chiller is static, you need just a small pump. And for all this reason, the return on investment for the customer was around 2-3 years. And I wanted to show you a small video about this installation. I hope it doesn't stop, but let me know if you can see this. In this video, we saw the installation of the absorption chiller that was connected to the heat recovery from the turbine gas and also to a cooling tower for the cooling of the machine. Here, just a picture of what looks like the touchscreen with the main basic data. So the external ambient temperature, the COP. Please note that the COP is 0.5 in this case, because we are speaking about thermal COP. If we consider, in this case of operation, the electrical COP, you can see that the tons of refrigeration are, in this case, was around 170, and the power consumption for the absorption chiller was way less, so around 13 kilowatt, because all these units are equipped with inverter on the pump, on cooling tower fans, on cooling tower pumps. What I wanted to highlight in this presentation is that at the moment, refrigeration is mostly based on compression chiller. So this means, especially for low temperature, that refrigeration consumes a lot of electricity. But we all know that in the end, electricity means a lot of CO2 emission in the atmosphere. And this is not so wealthy for the planet. So we wanted to highlight that there is an alternative solution, a sustainable solution to make refrigeration with low electric consumption. But in the end, also low electric consumption is not just a green thing. It's also about something economical, something that is very valuable. So in my opinion, to say all of this, I would like to resume in a sentence that is, why earn on behalf of our planet when we can earn by respecting it? So thank you for the time.
Thank you, Fabio. Very innovative system you have there. So one question I have is, definitely there's an electricity savings considerable with this absorption chiller combined with the CHP system, right? But the CHP system uses natural gas, which is burned, right? So if you look at the total emissions with the natural gas, how does that, have you done a calculation of that compared to, like, conventional refrigeration systems? And
yeah, I understand your point. Let's say this. Here in Italy, 3-generation systems are pushed a lot because are very efficient. They allow to have a reduction of emission of CO2. And for this reason, they have also some fiscal advantages. Let's say if you make a calculation, if you make a 3-generation, it means that you're producing electricity, making heating and cooling, and of course you have to burn natural gas. But if you make heating separated, so with the efficiency of a boiler, cooling separated with efficiency, let's say we calculated in this case from our measurements, an electrical COP on an early basis of around 2.5 the COP. With our system, we reduce of 10 times the consumption. So if we take in account all of this, the CO2 emission drops down.
okay. So if you break those three systems out in a normal sort of in a normal situation, compare the greenhouse gas emissions to your system has less greenhouse gas emissions.
Yes, it is, and also just as of course you know already that also it is good that ammonia and water is also a very ecological gas.
Right.
So also on this point is a very good solution.
Right. How much ammonia do you use in that case study?
Oh, in this case, we used okay, I can tell you in kilograms, but I have to make a small. It was around between 450 kilograms.
Okay.
But of course, also we need to take in account that also is water and ammonia in the most of the part. The ammonia is just in a small part of the system. So also on the safety side is good, also because we install this machine in open air. They are designed for external installation, and they are fitted also with, of course, ammonia detectors. So if there is also a leak, we detect it immediately.
Right. Okay. All right. So let's see. Are there any questions coming in, Franco? No, no
Yeah,
questions.
there's a couple there, yeah.
Are there?
You want me to read some of them?
Yeah, would you?
Yeah, so
Wait, what? Yeah, go ahead.
yeah, so Andy Baker has a question for John saying, could you make efficient use of waste heat rejected by TC CO2 system in summer with absorption or absorption chiller? Oh, I think you're on mute, John. John, I think you're on mute.
I'm unmuted.
There we go.
So the question was taking the heat from the transcritical system in the summertime and injecting it into the ammonia water absorption
Yes.
chiller as the heat.
Yeah.
Yeah. Yeah. No, you know, I had the same question after watching the ammonia absorption chiller, because especially with air cold, we can easily get to 200 and something degrees, 210, 220, depending on what the intermediate temperature is. So I don't know how much mass flow would be required, but it's definitely something worth looking into more. I know I plan to.
Okay, thank you, John. And there's another question here from Troy Davis for Fabio. You showed a 194 Fahrenheit driving hat water temperature in your example. What is your minimum inlet driving hot water temperature that you can operate your machine efficiently? Also, does your cooling tower water inlet temperature affect the COP of your machine? Nice looking package.
Oh, first, thank you very much for the question and for the comment. Let's say for absorption machines, we need 3 temperatures for the COP and the performance, and the temperatures are related together. So when we move one, another one moves. And the temperatures are cold temperature, for example, cold glycol, hot temperature, and condensing, cooling temperature. Let's say in our example, we saw that there was glycol at around 17 degrees. But we know also that we can run this glycol. We can make glycol at 17 degrees also with 170 degrees on the hot side. So let's say depends on the application and how we want to size the unit. So we have also installation here in Italy that are with motors, with engines, that are running with water, hot water at 170 degrees. But also depends, of course, if we are going to make cooling, for example, just a second, sorry, for let's say an ammonia system working at minus 30 degrees. So for example, for frozen products, we will need much higher temperature. So for example, the temperature will be around 340 degrees hot water. So let's say the lower the cold temperature we want to make, the higher the heat recovery temperature. Of course, reducing the cooling water from cooling tower helps in terms of efficiency. I hope this answered the question.
Yeah, thank you, Fabio. Franco, is there another one?
Yeah, I think there's one more, and I think it's for John. And it says, once you achieve the expected total of 20% savings, how would this compare to kilowatt hours per year to a conventional synthetic solution? More or less about the same. And this is from Michael Latinen. Sorry if I pronounced that wrong.
So the question was, I'm not sure I understood the question.
Yeah, he says, I'll read it again. Once you achieve the expected total of 20% savings, how would this compare in kilowatt hours per year to a conventional synthetic solution?
So one of the, and I'll just use the Albany site. So the climate in Albany, New York is very good climate for transcritical CO2. And because of the climate there, I can run at really low condensing temperatures for a lot of hours a year. So compared to conventional synthetic refrigerants, I would say that on the compression side, we would win by 15 or 20% most of the time. And this is pretty consistent. We see this in Canada, in supermarkets where the climate's very similar to Albany. I think on this site, Justin, you need to understand we're running dry, so we're not adiabatic. And typically in the US, we would have an adiabatic gas cooler to help carve out some of those summer days. So if I had adiabatic, I would even save more energy than what we're doing, but there's no water on site.
Okay, thank you. I want to go around with one final question to each of the panelists, and that is starting with Fabio. So your system that you talked about, your case study, how many of these are installed in Europe or around the world, and what are the prospects for this as a solution for industrial applications? I mean, is this fairly rare, or do you see potential for this growing?
Let's say this, as I mentioned, the technology is very old. It was replaced in the end with compression system because the electricity cost was small. The energy was cheap. But now we see that the energy prices are increasing every year. And this system allowed to cut these prices. So I see that the opportunities for such system are increasing every year, but we see on our own because we started, let's say, this product 7 years ago. We make a PhD degree on this, one of our employee. The first year was about studying. And then, let's say, every year we see this, we increase the production of the machines. So now at the moment, we have 17 machines, 16 in Italy and one outside. I know that in Europe, these machines are used. They are not so common, but we see that this is increasing because of the prices.
Mm-hmm. So you have 16 of these similar, what you just described, installed?
Yeah, of different kinds, because we go from a small machine, so let's say 30 tons of refrigeration, up to big machine, that means 600 tons of refrigeration.
Okay, thank you.
You're welcome, thank you.
John, transcritical CO2, we're seeing a lot of uptake in North America. I mean, there's been not a lot, but I know of several examples of it. Excuse me, in the U.S. and in Canada. What do you see as the prospects? I mean, some people think transcritical CO2 has got a big potential in the industrial space. What do you think?
Oh, I think it does. I mean, it's one of the other natural refrigerant solutions, right?
Yeah.
So I come from a company, we do ammonia and CO2, and we think that they're both great solutions. And sometimes the sites don't allow, or the state doesn't allow ammonia, or struggles with it. And when I look at what we're replacing and going after today is synthetic. And so I think a lot of traction with transcritical CO2. I thought it used to, when I started in this 4 years ago, it was kind of limited to the colder climates. The technology continues to develop, not only on the ejector side or the mechanical subcooling side, but we're just getting better at making the systems more efficient. So I see it in ammonia, as the solutions going forward.
Okay. Kurt, the low charge systems have grown over the last few years. I guess you could say both stick built and packaged. What growth have you seen in the package side, and compared to the stick built, and how do you see it developing?
Well, it's definitely evolving in a growth pattern. We've got approaching 100 units out there now in the field. 20% of them are the chiller, packaged secondary fluid chiller that I just presented. The other 80% is the penthouse package, and there's more products to come. The technology is finally really starting to be adopted at a quicker pace. COVID, with the development, as I said, 60% of the projects are greenfield, large capital investment projects. COVID is the market at the beginning of this year was really off to a gangbuster start. COVID has slowed it down, but there is now what's happening, a pent-up demand with a lot of capital projects that I think everybody in the industry is pretty excited about the light switch being turned back on with larger capital projects that have been on hold, and picking up the accelerated adoption of these packaged low charge units. Now, as it relates to central low charge ammonia system, that is evolved too.
Yeah.
I was talking to one of our representatives the other day who told me that, a typical central plant ammonia system, to pick a number, maybe 60, 70% of that type of project is focusing on what they would call low charge central system, just focusing on reducing the quantity of ammonia. Even in a central system standpoint, it will still have much more, and quite frankly, may easily fall over the 10,000 pound threshold from a regulatory standpoint. But nonetheless, the industry has really shifted to focus on reducing the quantity of ammonia charge in any system.
Right. Does the low charge package approach address a lot of the safety issues around ammonia and allow installations, in areas that are more populated?
Absolutely. Of that installed base, several of them are in urban areas where the owner definitely felt that the significantly lower amount of ammonia made a real difference in proceeding with the project. We have a tool, in the ammonia world for compliance. EPA requires an offsite consequence analysis. And with low charge ammonia, there is no offsite consequences. We have sample modeling in a couple sample projects where an ammonia release, which would worst case be the entire charge of a package. I think Bob mentioned that earlier. So a total worst case might be 300 or 400 pounds and up on the roof. It doesn't even make it to the property line quite often. So there's no offsite consequences as compared to the old larger ammonia systems that would potentially impact the neighbors. And so urban settings clearly are, from an ownership standpoint, see it as a big reason for pursuing the solution.
Right. Well, it's going to be interesting to see, how these different systems compete, the low charge package systems, the transcritical CO2, and now even the absorption ammonia chillers tied in with the CHP, power systems. It's going to be interesting to see how these compete and how they, how it plays out, which will be installed and which kinds of applications and sites and so on. So, but I think, natural refrigerants clearly, providing the industrial sector with some interesting and really good options.
I see it changing in front of my eyes. It used to be that the package would compete against a central system. Now we're starting to see package supplier competing against package supplier.
Yeah.
If I might say also about absorption chiller, I mean, I think it's not a compete because they work together with refrigeration plants and they work together also with a package system, because most of the installation we made, let's say also the absorption chiller was making the base load of a good part of a load, and the compressor were covering the peaks. So let's say they are good friends with big plants and of course also with a package system.
Oh, so you're installing those alongside of compressor systems?
Yeah, they are very flexible because, for example, we made an installation with glycol, like we showed, but we made the installation also with ammonia plants working at, around, minus 40 degrees ammonia. So we were taking ammonia gas and we were liquefying. But it was separated, ammonia plant and ammonia of absorption chiller. So we were like making work in parallel with a normal refrigeration. We work also with a CO2 systems. There was this an installation in which we have a cascade system, ammonia to CO2. And with our unit, we were condensing the CO2. So let's say they are flexible. They fit with every kind of unit.
They also work by themselves as well. Like in this case,
yes, they also work by themselves.
The case study was by itself.
The case study in this case was parallel with an existing unit.
Oh, it was parallel with the existing.
Yeah.
And what refrigerant did the existing unit use?
The existing unit was, I think, R404A or R410A.
Okay, so it was working together with that one. Okay, was it already existing system? And
yeah.
And they installed this additional. Okay. All right. Well, on that note, I'm going to conclude the session. I want to thank our excellent speakers for participating today, presenting these different scenarios. I hope it was valuable to our audience. And if you have any further questions, you can reach out to them individually. And I want to thank you very much, guys. It was very interesting. Thank you. And we'll have I guess Mark Chastero will be doing a concluding remarks in a few minutes. Is that right, Franco?
Yeah, that's correct. We'll have like a super short 3-minute break, and then he'll do some short concluding remarks.
Okay, so a round of applause for our speakers. And thanks again, guys.
All right.
Thank you very much.
Thank you.
Take care.
Bye-bye.